Okay, so we'll finish up section 3.2, and these are just some theorems about um, uh, equality of subspaces. So what they're getting us ready for is the idea that we can represent the same subspace in lots of different ways, and it would be nice to know when, even though we have two different representations, we have actually the same subspace. So I'm just going to kind of go through their stuff. So it's nice. They have a lemma, 3.2.1. And so again, a lemma is a theorem, but it's usually a theorem that is used to establish another theorem. And so in this case, they say, suppose each vector, okay, so each of x1, x2, up to some xr is a linear combination of some other vectors. Okay, so it's a linear combination of y1 through ys, so y1, y2. Now, a couple subtle things here. Notice we have an r for the x's and s for the y's, so that these don't have to have the same number of vectors. Okay. So then, if this is the case, then any linear combination of the xi's, so x1 through xr, is a linear combination of the y's. So, and I think we'll do a proof of this. The text does not. So of the i's, well, or maybe I'll use yj's. The textbook doesn't do a proof of this, but it's pretty straightforward. I don't remember. Maybe it's a problem, so one of the problems, and so maybe I'm giving an answer to one of the problems. But the proof. So what are we told? Suppose each of the xi here are linear combinations of the y's, and so what that means is, suppose I'm going to do the proof with matrices. So I'm going to make a matrix Y, which is made up, its columns are the vectors y1, y2, all the way to ys. Okay, so what that means then is that each of the xi's, so it's a linear combination of those, I could write this as a given xi, so I'm going to write it though this way. So I've got a matrix times, now I'll use a vector c, c1, and that is equal to x1. Okay, because remember that if I just want to take a linear combination of the columns here in y, all I have to do is multiply by some vector on the right, and that will give me linear combinations of the columns. That's the column space. Okay, so we have that. We have yc2 is equal to some x, our x2 and so forth. So I don't know what the C1, C2 are, but they exist because we're told these things are linear combinations. And so I'll do my CR equals XR. Okay, so now suppose, I make a matrix X, which is, X1, it's all the columns of X, XR. And now, I guess here's also a subtle thing is that you may not jump right out at you is, again, there may be a different number of columns here, a different number of vectors, but actually all these vectors are the same dimension, so maybe dimension n or something like that. But the number of rows here is the same for all of these. Okay, so now it says then any linear combination of the xi's is a linear combination of the y's. Okay, so suppose I take a linear combination of the x's. Well, so x times some linear combination. I use c's before. Well, actually, sure, I can just use a c vector, not a ci vector. So here is a linear combination of the x's. And the question is, can I show that that's a linear combination of the y's? Well, so what I've done is I've taken a C1. Now notice this is the real number C1, not the vector C1. X1 plus C2 X2 plus all the way to my CR XR. Okay, but now I can substitute in, and maybe C wasn't the best choice in hindsight here or something. But that X1, remember that I can write that as the matrix Y1. So this is C1 Y times C1 with a bar over it. So like I say, maybe C is not the best choice. So hey, that was an A. Can't fool me. Those were all A's. Okay, so I have an A1, C1, and then similarly an A2, Y, C2, plus all the way out to an A, R, Y, C, R. But now I can use my properties with the matrices and in scalar multiples and so forth, that I can write this. Actually, I can fit it here, I guess. So yc1 is just a vector, and yc2 is just a vector, and so forth. So I just have a linear combination of those vectors. Well, I can take that and make this, let's see. Actually, I got to think about this now for a second. That's a C. And, yeah, I think unfortunately to really get anywhere, I have to do kind of like I did with the X and write all these darn things that way. Otherwise, I can't really just throw them together and say, look, I did it. So unfortunately, I think what I have to do is take the A1 and then this Y1, C1. Oh, now it's a very good reason to have switched to the A's. So, this is my C1, 1. Okay, so the first component of C1 times Y1 plus the second component of C1 times y2 plus the third component of C1. So, we get this idea, and there were let's see, there would have been S components of the C's. So C1S, YS. Okay, so we get that, and then plus, similarly, A2. And unfortunately, I have to keep writing all this stuff out. C21. This is just, no wonder they didn't prove this, right? It just takes a lot of room to do it. Okay, all the way out to C2S YS. Okay, and I need to take that all the way out to the AR. So, this just keeps going, and then AR times C, what are we at? R, yeah, R1, Y1 plus CR2, Y2 plus, and we write all those out, CRS, YS. Yuck. Okay, so now you see I can multiply through by the A's and collect up like terms in terms of the vector yi for each of these, y1, y2, and so I end up with an A1 C11 plus an A2 C21 plus all the way out to an AR CR1. And that's all times Y1. And then I have the next one, A2 C21 plus, oops, sorry, A1. I was looking at this A2 here, but it's, I had to start with A1 up here. And so it's A1 C12. Now I get to this next line here. So now I have my A2 C22, and then plus dot dot dot, all the way to AR CR2, and that's times Y2. And I keep doing that all the way, oh, that should be a plus. And then plus my last row, so I have AR CR1. Whoops, I did it again. I'm looking at that instead of where I should be looking. So I have my A1. Oops, didn't erase enough here. Okay. So top row, I have that oops. Let me try that again. A1. Okay, so back here, I'm looking at the top row first, so it's A1 times C1S plus A2 times C2S plus, and I keep going down those rows until I get to the last one, AR CRS, and that's all times the YS. And so there I have my linear combination of the Y's. And so, if I really worked at this, I might be able to clean this up by sort of turning all these C's, the collection of those C's, into a matrix, and then I might be able to stay out of all this component-wise stuff that we have in here in order to make a cleaner argument. But nonetheless, here we get through our argument and we have a linear combination of the Y's. And again, that's what we were supposed to show, right? suppose each of the x's is a linear combination of the y's, then any linear combination of the x's is a linear combination of the y's. And so I've shown that. I started with a linear combination of the x's and got to a linear combination of the y's. Okay, so that's that lemma. And actually that took a while, so I think I'll just stop this video and then go on to some more theorems.